Now we are in chapter 10. This is the last chapter we will cover in this course, and chapter 10 is on correlation and regression. Now within chapter 10, we only have 3 sections remaining. We're going to cover 10.1, 10.2, and 10.4. Now for 10.1, the topic here is correlation. In this section, we'll introduce the linear correlation coefficient, or R. This R will be a number, and we'll be able to calculate that. It'll be a measure of how well paired sample data fit a straight line pattern when graphed. Paired sample data, what does that mean? Well, we're used to seeing X and Y data, so that's our paired sample data, where one pair is one X value and one Y value. Now, along those same lines, we'll use the sample of paired data, which is also sometimes called bivariate data, where bi meaning two, variate similar to variable, so bivariate just means that we have 2 variables. And we're used to working with bivariate data when we have our typical graphs where we have an X variable and a Y variable. Now you may have also made 3D plots where you introduce a Z variable, but here we have bivariate data, so just 2 variables. We'll use that bivariate data to calculate a value for R, then use that value for R to decide whether there is a linear correlation between those 2 variables. So again, we're focusing on the linear correlation between those 2 variables. As we consider only linear relationships, which means that when graphed in a scatter plot, which we've done before in an Excel assignment, the points approximate a straight line pattern. Now you may have seen sigmoidal graphs, you may have seen logarithmic graphs. Again, here in 10.1, we're only focused on a linear relationship between our 2 variables in our data. And by linear, it means we're looking for a straight line pattern. Then, as we saw in chapter 8, we talked about conducting formal hypothesis tests. So towards the end of 10.1, we'll tie in what we learned in chapter 8, specifically to linear correlations. So what we'll do is learn how to conduct a formal hypothesis test that can be used to decide whether there is a linear correlation between all population values for those 2 variables. So maybe you can start to guess what our null and alternative hypotheses will be. So we'll do that at the end of 10.1. A heads up for those 2 hypotheses, we might start to think about, is there a correlation between our sample data, or is there not a correlation between our sample data? Now let's lay some groundwork here. So let's define a correlation and a linear correlation. So generally speaking, for a correlation exists between 2 variables when the values of one variable are somehow associated with the values of the other variable. So a correlation, it's pretty general, but here in our data, one variable is somehow associated with that other variable. Now, correlation is the broader term, and as I mentioned in 10.1, we're focused on looking at linear correlations. So similarly, but more specific than a general correlation, a linear correlation exists between 2 variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. So not only is there association between one variable and the other, but when they're plotted, those data actually resemble a straight line pattern. Now we'll practice taking a set of data, making a scatter plot from that data, and then interpreting, is there a correlation based on the visual appearance of our scatter plot. Before we make a scatter plot, let's look at the different possible patterns we can see when we have a scatter plot already available to us. Let's start out with A here. So for a positive correlation, we have an R value of 0.859. When we plot data that lead to an R value of 0.859, it could look something like this. Again, our x-axis is here on the horizontal and our y-axis is here on the vertical. When we plot our data in a scatter plot like this and we get a pretty general straight line pattern, this is considered a positive correlation. How can we tell that? Well, visually we can see that as X increases, Y also increases. So that's how we think of a positive correlation. So X is increasing and Y is increasing. We can also tell, other than visual inspection, that our R value is 0.859. So this is a positive correlation because it's a positive value for our R value. It's also a fairly strong correlation because this value for R is fairly close to 1. We'll cover this in more detail, but the maximum value that R can be is +1. So characteristics of this positive correlation is that we do have this distinct straight line or linear pattern. And again, another way to tell is that if we have a positive linear correlation between our X variable and our Y variable, so again, we do have this bivariate data. As the X value increases, the corresponding Y value also increases. So we can have a negative linear correlation. Here, though, we see a positive linear correlation, again, because as X increases, Y increases. Now let's take a look at a negative correlation. So here we see a scatter plot. We have our X data, we have our Y data. Here, though, we see this data goes kind of towards the right of the screen. So by visual inspection, we can see that as X is increasing, the Y values are actually decreasing. They're getting more negative. So that's by visual inspection. Then by our linear correlation coefficient, or R, we can also tell that we have a negative correlation because this value is negative. Now on the other end, the minimum value that R can be is a -1. So this is a fairly strong negative correlation because this value is pretty close to -1. So far with a positive correlation and a negative correlation, we still have this distinct straight line or linear pattern. For a positive correlation, we saw it kind of go towards the upper right of our data. For this negative correlation, we see the data sort of trends downward or to the bottom right of our graph. So because for a negative correlation, we see that as X values increase, our Y values actually decrease. This is why we say there is a negative linear correlation between X and Y. Again, because as X values increase, the corresponding Y value actually decreases. For example, let's say that our X value is 2, we go up to the Y axis here, and maybe that corresponding Y value is about -8. So that point would be 2, -8. Let's try another one though, to see if we do follow this negative correlation pattern. Let's say we have an X value of 8, then we go up here to the Y axis, and maybe that Y value is about -38. So we had 2, -8, then 8, -38. As X increases from 2 to 8, our corresponding Y values decrease from -8 to about -38. So positive versus negative correlation, we can tell by visual inspection. We can actually look at the R values if they're available to us. Or we can try doing what I just did, where we match up an X and Y value, then we match up another X and Y value, and we see as X increases, is Y increasing or is Y decreasing? Again, if X is increasing and Y is increasing as well, that's a positive correlation. But if X is increasing and Y is decreasing, then that's a negative correlation. Now, the next example we'll look at is when we have no correlation. So by visual inspection, here again, we have our X-axis, we have our Y-axis, and all of our data points are pretty randomly scattered throughout. I can't really distinguish a straight line pattern here, any which way I look. So for no correlation, you can tell by visual inspection and also by our R value, where no correlation would be an R value of equal to 0. Now, this R value of 0.074 is not quite 0, but when we remember our scale, that -1 is when we have a strong negative correlation, And then +1 is when we have a strong positive correlation. Then a value of 0 in the middle is when we have absolutely no correlation between our data. So this isn't quite 0, but it's almost 0. And you can really see that there isn't really any correlation between our X and Y data. So by visual inspection, there's no distinct pattern. Our R value is pretty close to 0. These two things suggest that there is no correlation between X and Y, between our bivariate data. Next, now I mentioned in 10.1, we'd be focusing on linear correlations here. So this other type of correlation can exist. It's a nonlinear relationship. We can still get an R value from nonlinear relationships, but you can see that this visual inspection does not lead us to believing this is a straight line pattern or a straight line correlation. Looking at the R value can be a little tricky though, because this could imply that we have somewhat of a positive correlation. However, this R value is probably from these initial points here that do resemble a line. However, our whole data set is all of these points combined. So here we have a nonlinear relationship, not a linear relationship. That doesn't take away from the association between the X and Y data, but the X and Y data as a whole definitely have a nonlinear relationship. And again, in 10.1, we're focused on these linear correlations. So from this, you can tell to be careful just by looking at the R value, that we can't always say, well, okay, an R value of 0.330, that's probably a mildly positive correlation. Although that may be true, that's not a positive correlation, that's a linear correlation, and that's what we're interested in here in 10.1. So anytime we say that bivariate data have a nonlinear relationship, we say that there is a distinct pattern suggesting a correlation between X and Y, but importantly, the pattern is not that of a straight line. So while we're focused on straight line correlations in 10.1, that's not to say that these nonlinear correlations do exist as well. So now here are all these graphs put together, and now we're going to talk about measuring the strength of a linear correlation when we know that value for R. So we use the linear correlation coefficient, or R, which is the number that measures the strength of the linear association between the two variables, X and Y. So within each of these values, we can get a measure of the strength of the linear correlation. So when looking at these values, we want to look at the magnitude of our R value and also the sign of our R value. The magnitude of that R value actually tells us a measure of the strength of the linear association between the X and Y variables. Now, for instance, just focusing on the magnitude here, we have an R value that's close to 1, but it's 0.859. Because this R value is positive, we have a positive correlation, and because it's fairly close to 1, we have a fairly strong linear correlation. Looking at B, though, in comparison, if we take away the negative sign and we're just focusing on the magnitude, then we compare 0.971, which is even closer to 1 than is 0.859. How does this match up to what we see visually? Well, here these points are pretty close together and they look like a straight line. Here with an R value that has a smaller magnitude, we still see the straight line, but the data points are more spread out. So a magnitude of 0.971 has a stronger correlation than a magnitude of 0.859. Again, it's whatever number is closer to 1, either positive 1 or negative 1, that tells us the strength of the correlation. Then again, because an R value that's equal to 0 indicates no correlation, then this R value for plot C of 0.074 matches up to what we'd expect for a no correlation example. It's not quite 0, but it's pretty close to 0. Then again, we need to be careful with these nonlinear relationships because from the R value, we could say that there is a mildly positive correlation. By visual inspection here, though, we see that there isn't just a linear relationship between the data. We sort of have a start to the linear relationship, but then this curves around to be a nonlinear correlation. So again, we can look at our R value to tell us the strength of the linear correlation, but we need to be careful in cases like this where we have nonlinear relationships that can still produce an R value that's not 0. And again, the possible values for R now is that it can range from -1 to +1. -1 being a perfectly negative strong correlation, and +1 being a perfectly strong positive correlation. Where an R value of 0 again is that we have no correlation. Our possible values for R then can range anywhere from -1 up through +1, including the value for 0. So now that we know the different possible values for R, let's next talk about how to calculate those. So within this next portion of 10.1, we're going to learn how to calculate and interpret the linear correlation coefficient, R. Now, the objective for calculating the linear correlation coefficient, R, is ultimately to determine whether there is a linear correlation between the two variables that are in our sample data. So this is saying if we want to know if there is a linear correlation, then we should calculate this linear correlation coefficient, R. Now there's some slightly new notation to learn for calculating R, so let's go through that now. N that we're used to seeing for the number of samples, importantly N is a little bit different here. So rather than N being each individual sample data, N here is the number of pairs of sample data. Where if we have XY data where 1, 2, that pair is considered one value for N. So again, we don't look at the total number of X and Y data, we just use N to say the number of pairs of data. Then we've seen this notation before, but not for a little while. So here's capital sigma, which denotes a summation. In other words, this sigma denotes the addition of all the items that are maybe within parentheses or just come after that sigma notation. And again, we should practice saying this in the correct way, so we're going to call this sigma moving forward. Now let's combine notation now. So if we have this sigma in front of X, that means that we will do a summation or add all of our X values. So sigma of X, the summation of all the X values. For these next two notations, we need to be really, really careful about our order of operations. Here we see the summation or sigma of X squared. What this means is we need to first square all of our X values, then we add up the products of squaring each X value. We'll practice doing this in 10.1, but again, first we want to square all of our individual X values. Then the product of squaring all of those, we will add up together. We will sum all of those products. Next, pay close attention to these parentheses. So first here, we would add up all of our X values, then square that. So again, here this notation indicates that the X value should be added first or summed first because this portion is in parentheses. Then the total of all of this is squared. Really, really importantly, this notation here is very different than this notation here. We will practice doing both of these in 10.1. And another reminder here, pay very close attention to the order of operations, both for this notation, and we'll see one additional piece of notation on the next slide. Now, here's the notation continued. This is the one I mentioned that we also need to be careful about for the order of operations. What we see in this notation is a sigma or summation symbol. Then we have X times Y after that summation symbol. This means that we first multiply x by y, and we do this for every single pair of sample data. So we take our x value, multiply the x value by the corresponding y value. Then once we have all of those products of x times y for each pair of data, then we sum all of those values. And again, this asterisk here means to be really careful about the order of operations. Now, another point to be careful with is that R, which we've seen throughout, is the linear correlation coefficient, but for sample data. Remember the clear difference between a sample and a population. So again, R is our linear correlation coefficient for sample data. So what's our symbol notation for population data, you may ask? Well, it's this symbol here, which we pronounce as rho. If you calculated density before in a chemistry class, for example, then you would have seen this notation that we pronounce as rho. So rho is the linear correlation coefficient for a population of paired data rather than sample data. So again, R for sample data, rho, not P for population data. And again, here I warn you to pay very close attention to the order of operations for all of our summation notations. So next, still in this topic of calculating and interpreting the linear correlation coefficient for R, we're going to talk about some requirements. We'll go through the full list of requirements on the next slide. Here is an important preface to those list of requirements. So as we saw for the nonlinear correlation, we could calculate a value for R. So theoretically, given any collection of sample paired quantitative data, the linear correlation coefficient R can always be computed. So, okay, we can calculate a value for R, but remember we want to connect this back to a linear correlation coefficient. So we'll go through the list of requirements on the next slide, and those following requirements should be satisfied when using the sample paired data to make a conclusion about the linear correlation specifically in the corresponding population of paired data. Why is this wording of population here? Well, remember what we've been doing throughout the semester. We can take sample data from a population in order to make inferences about that population. So ultimately what's being said here is although we can always calculate R for any pair of sample data, quantitative data to be specific, it does not mean that we have a linear correlation. So what we need to do is calculate a value for R, then check all the requirements that are listed on the next slide. Only if those requirements are satisfied can we then make a conclusion about linear correlation specifically. So we're not just going to calculate and look blindly at our R value, we're also going to very carefully look at these next requirements. Requirement number 1, the sample of paired, usually XY data, is a simple random sample of quantitative data. Our data have to be unbiased, they have to be collected randomly. Sometimes it's difficult to tell if we're given a set of data to work with, if that really was collected randomly, so we'll talk a little bit about that in the example we go through. Requirement number 2, visual examination of the scatter plot must confirm that the points approximate a straight line pattern. Again, like we saw for the nonlinear correlation, we saw a value for R that seemed somewhat convincing, but upon visual examination, we saw that that really wasn't a straight line pattern. Requirement number 3 deals with outliers. So because results can be strongly affected by the presence of outliers, any known outliers must be removed if they are known to be errors in the data. What's nice about calculating R is we can do this fairly quickly in Excel. So one thing we can do is calculate R with the outliers present and then try to take them out of our sample data then recalculate R and see the difference between the R values. Again, outliers will strongly impact our value for R, but if those data points aren't really outliers, then we won't see much difference between our R value pre-outlier removal and post-outlier removal. Now, as we talk about requirement 2 and 3, these are actually somewhat simplified attempts at checking this formula requirement that we usually see in statistics. That formula requirement is that the pairs of XY data must have a bivariate normal distribution. By checking requirements 2 and 3, we're getting at this formula requirement, so that's what we'll do in the scope of this class. Again, as we're checking 2 and 3, we're essentially checking if our bivariate data follows a normal distribution. Now, I mentioned there's a somewhat straightforward approach to calculating our value for R in Excel. There's also formulas we can use to calculate R. Now, we'll break down this formula. We'll also practice using it. So let me show you what it is. For formula 10.1, it looks like this. It looks complex, but when we break this down, we see that we only need a value for n, so the number of paired sample data. Then we need our values for x and our values for y. With different variations of how we use our x data and our y data, we can put all this together to then calculate a value for R, our linear correlation coefficient. So that's formula 10.1. We'll practice using it. Now for formula 10.2. It looks a little less complex, but now we've introduced this z value here. So in order to use formula 10.2, we need n again, but we also need this z subscript x and that z subscript y. So what these are is that the z subscript x denotes the z-score for an individual sample value of x. And then z subscript y is the z-score for the corresponding sample value for y. This actually ends up being slightly more complicated than this one, depending on how you look at it, because you have to get a z-score for all of your individual x data and all of your individual y data. We'll practice calculating R with formula 10-1. We'll also practice calculating R with this formula 10-2. Before we do those examples, let's also talk about how we round the linear correlation coefficient R. For these R values, get used to rounding to 3 decimal places. Next, we're talking about the interpretation of this linear correlation coefficient, or R. We talked about the possible values for R, but now this is getting into the actual interpretation, so let's talk about it. For this portion of the interpretation, we can use a p-value. Now, you probably remember p-values the best as we worked with in Chapter 8, but we actually saw p-values originally in Chapter 2. So now, as you're planning on studying for finals and you encounter p-values again in 2.4, you'll more easily recognize, hey, I know what that is. So then once we have a p-value, we'll also then compare it back to our significance level, or alpha. This will look similar to what we did in Chapter 8, but again, here, remember, we're focusing on these linear correlations. So in this case, if the p-value is less than or equal to our significance level alpha, then this supports the claim of a linear correlation. Then for the other case, if the p-value is greater than alpha, then this does not support the claim of a linear correlation. We will talk explicitly about how to calculate a p-value for Chapter 10.1, these linear correlations. It's a little bit different than Chapter 8 and how we learned to calculate a p-value there with hypothesis testing. Again, because these p-values here in 10.1 will be for linear correlations specifically. So that was interpretation with a p-value and a significance level alpha. There's another way to interpret linear correlation coefficients, and we'll practice this way as well. So we'll practice using table A6 and consider critical values from that table as being both positive and negative. So once we know what that critical value is, then we can make these different interpretations. In order to say if there is a correlation or if there is no correlation, we need to compare our R value, our linear correlation coefficient that we find, to a critical value. And again, we can find these critical values using table A6. We'll talk more about absolute value here in 10.1. So if the absolute value of R is greater than or equal to our critical value, then we conclude that there is sufficient evidence to support the claim of a linear correlation. Alternatively, if we find our critical value using table A6 and we compare that to our linear correlation coefficient R, and we find that the absolute value of the linear correlation coefficient R is less than our found critical value, then we conclude that there is not sufficient evidence to support the claim of a linear correlation. So for this method of interpretation, we still need our R value, but now we need a critical value to compare that R value to. If you have not seen the meaning of absolute value in a little bit, remember that if we see these bars here, these lines around R, this means that we're taking the absolute value of R. Recall that absolute value means the non-negative value. Now, for example, if we found our value for R and it's negative 0.89, in order to use this method of interpretation, we first need to take the absolute value of R. When we take the absolute value of negative 0.89, then we consider that as just positive 0.89. So again, for this critical value of interpretation, we always need to take the absolute value of our R value first, then compare that to our critical value. Now, as I mentioned, we will practice using table A6 to get our critical value, then compare that critical value to our R value. Table A6 can be found in your textbook. It's on page 742. What you'll see in table A6 is this column here on the left. That's N. Remember, that's our number of paired sample data. Then the two other columns show an alpha value, a significance level of 0.05 and 0.01. We'll talk about what value to use for N here, and then it depends on what significance level, if you have 0.05 or 0.01, for which column we look at. We'll practice doing this later in 10.1. Now, before we get into some examples, we're last going to talk about some properties of this linear correlation coefficient, R. Property number one, we've talked about throughout, so the value for R is always between -1 and +1. The possible R values are inclusive here, meaning it can equal -1 and it can equal to +1. In symbol notation here, our R value can be greater than or equal to -1, or it can be less than or equal to +1. Remember, R can also be equal to 0. That means we have no correlation. Property number two, if all values of either variable are converted to a different scale, the value of R does not change. One example of what's meant by scale here can be seen by looking at a real horse and then a horse drawing. Now, a real horse might have these dimensions of how tall they are and how long they are. But when we're drawing a horse, we wouldn't be able to draw this scale unless we were doing a mural, for example. So in order to scale the real horse properly for a drawing of a horse, we could go from 1500 millimeters to 150 millimeters, for example. Then to be consistent with dimensions, we'd have to go from 2000 millimeters to about 200 millimeters for the length of our drawing. This is an example of a scale of 1 to 10, so just an example here to emulate this property of our linear correlation coefficients, R. So essentially, if we took all of our x values, we multiplied those by 10, we did the same for all of our y values, then our value for r would be the same before scaling up and after scaling up by a factor of 10. Property number 3, the value of r is not affected by the choice of x or y. Meaning that if we interchange all x values and all y values, the value of r will not change. To illustrate this property, I went and I made a scatter plot based on these x values and these y values, where first I plotted them like this, then I switched all my x and y values and also plotted that data. As a reminder for making scatter plots, you can put in your data like this into your 2 different columns, then you highlight and select all of your data. Keep in mind this would be one data set and this would be one data set, so I'm just highlighting this portion first. Then in Excel, I go to Insert, Scatter Plot, then click on the graph for a scatter plot. That will populate a scatter plot, cause that to appear on your Excel spreadsheet. Then when we click on our newly populated scatter plot, we can go under the Chart Design tab, go to Add Chart Element, click on Trend Line, then go to More Trend Line Options. Then a set of different options will appear. We can go to Trend Line Options, click on Linear, then go to Check Off Display R-squared value on chart. Now, importantly, when you do it this way in Excel, this gives you your R-squared value, not your R value, not the linear correlation coefficient, R. However, R and R-squared are related. We'll talk about that as well in 10.1, so let me continue on with showing you this example. Now, before I show you the scatter plots, I also want to remind you that the title is always your vertical versus your horizontal axes. And when you want to make a scatter plot in Excel, you want to set up your columns to have your horizontal axis values on the left-hand side, and then your vertical axis values on the right-hand side. So for my x values here, and these being my y values, this should populate a scatter plot that looks like this. My x values were initially on the left, now they're on my horizontal axis. My y values were initially in this right-hand column, now they're on my vertical axis. After I made this scatter plot without this trend line here, I followed these steps to then show my trend line and my R-squared value on the graph. I also want to point out for your title, if this were really the month and then the corresponding snowfall, then we really put snowfall versus month. I'm keeping this generic here as y values versus x values because we don't have anything specific to put in. For graphs that you make though, where we do have something specific, then you should retitle this as, again, snowfall versus month. So as these are my x values, these are my y values, I got an R-squared value, again, not an R value, but an R-squared value of 0.9877. Then I switched them. So I took my y values, I put them here under my x values, and I did the same for my x versus y values. When I plot this, I get a different looking graph for my scatter plot, but then I put in this trend line and I added an R-squared value, and it turns out that these both have the same R-squared value. So for this property number 3, we can see that truly this is the same R-squared value as this when we switched our x values and our y values. So be sure to practice making scatter plots on your own, adding in these trend lines, adding in these R-squared values. Also keep in mind, we should always label our y-axis and our x-axis and add in a descriptive title. So be sure to practice this, look back at past Excel assignments, and let me know if you have any follow-up questions to making these scatter plots and adding these linear trend lines using Excel. Continuing on now to property number 4, our R value measures the strength of a linear relationship. Again, this has been mentioned throughout. It's not designed to measure the strength of a relationship that is not linear. So although we can calculate an R value for any set of paired quantitative data, the R value is really only designed to measure the strength of a linear relationship only. Property number 5, also as alluded to, R is very sensitive to outliers. This is such that a single outlier could dramatically affect the value for R. Now, sometimes it's difficult to say based on visual inspection if we do have an outlier. Here's an example where we have our scatter plot, we have a linear trend line, then this value here is a pretty obvious outlier. If we wanted to know if this really was an outlier, we could include all of our sample data, get an R value, then exclude this potential outlier, then recalculate the R value. If those R values are very different, then this indeed is an outlier. And again, if data points truly are outliers, then we should exclude them when calculating a value for R, our linear correlation coefficient.